Welcome. In this tutorial, we're going to be reviewing some basic ideas behind metal bending theory. The first concept to introduce is bend allowance. You may be wondering, what exactly is bend allowance? When a sheet is bent in a press break, the region of the sheet close to and in touch with the punch elongates to compensate for the given bend. For example, if you compare the length of this part up here before the bending and after the bending, you're going to find that they're different. As engineers, if we don't compensate for this difference, the final product or part won't have accurate dimensions. And of course, this becomes more and more critical for parts where tighter tolerances are required. Same thing goes if your parts require a very high level of precision. In this chapter, I'm going to cover some of the basic principles that engineers face every day in their work situations, so don't worry, this video is by no means an exhaustive discussion on metal bending theory. And I don't want to bend your brain, I just want you to understand what you're going to need under your belt in order to make the best choices. Before we get any deeper, let me clarify something. There isn't exactly a scientific method for predicting the exact bend allowance due to the many variables at play in the bending situation. For example, actual material thickness, tooling conditions, forming methods, and so on. There are so many variables. In reality, many different methods are used. Different methods will work for different situations and different engineers. As you can imagine, trial and error is a very popular method. In addition, engineers use bending tables that they've taken from their textbooks or that they're able to get from their metal suppliers and manufacturers. Some companies develop their own bending tables based upon their own standard formulas and so on. Now let's take a look at how we can calculate bend allowance. The bend allowance is based on the following formula that you see up here. The total length of the flattened sheet is equal to the sum of lengths 1 and 2 plus the bend allowance. The bend allowance is this curvy region here. I've got it shown in green. This region is where theoretically all deformation occurs during the bending process. That's why bend allowance varies for each combination of material type, thickness, bend radius, bend angle, and different machining processes, machining types, machining speeds, etc., etc. The list of variables is indeed extensive. And of course, for that reason, calculating the bend allowance by trial and error remains a pretty popular method. The value of bend allowance that is derived from textbooks or from manufacturers and suppliers is usually provided in table format and looks like what I'm pulling in right now. The bend table approach to calculating bend allowance is probably the most accurate method because you can input the data manually. If you're not sure of the bend allowance value, you can always run tests. For example, take a piece of shredded metal that you'd be using for this part, identical to what you'll be using for the machining. Then you bend it using the identical process that you'll use during machining. Then you'd take your measurements before bending and after bending. Based on this information, you'd adjust the bend allowance as needed. Another method is called the bend deduction method. Here's the formula. The flattened length of the part shown right here equals D1 plus D2 minus the bend deduction. As with bend allowance, bend deduction comes from the same sources, tables, testing, etc. Obviously, it's easy to see how these methods are related to each other based on the formulas that I've got up on my screen now. There's another method for calculating bend allowance and bend deduction. It uses what's called the K-factor. The general principle of the K-factor method goes like this. The neutral axis you see here is in white. The material inside the neutral axis will compress. The material outside the neutral axis will stretch. The neutral axis itself will be closer to the inside bend, as you see here in black. The more the part bends, the closer the neutral axis will lie inside the part. Take a minute to rewind that bit of this video in case it didn't sink in the first time. Once you've got this concept under your belt, it'll be pretty easy to understand. The K-factor is calculated like this: small t divided by big T. Small t is the offset distance of the neutral axis, and big T is the thickness of the material. With these variables, the formula for calculating the bend allowance for K-factor is noted as follows. BA, that stands for bend allowance, equals pi times A, that's the bend angle, divided by 180, multiplied by the sum of the bend radius inside the bend, plus the K-factor multiplied by capital T, or the thickness of the materials. In theory, the K-factor can range from anywhere between 0 to 1, but its practical uses range from about 0.25 to 0.5. For example, you'll find that hard materials like steel have got a higher K-factor, like 0.5, whereas softer materials have got a lower K-factor, closer to 0.25. Copper is one example of a softer material. In this chapter, you've heard me bring up terms like K-factor, bend tables, etc. In our subsequent tutorials, we're going to be covering these concepts in more detail, learning how to apply the K-factor, etc., using and creating bend tables, etc. One last point I wanted to bring up here. Let's take a look at my model. Different degrees of bends have different K-factors. The wiped hem on this part has a K-factor of something like 0.3. On the other hand, a softer or gradual bend, as you see on the other side, has a higher K-factor of about 0.5. And this concludes our tutorial on some of the theory behind sheet metal bending.